We're going to review some of the main results of quantum mechanics in order to continue our discussion on magnetic moment. So we'll start with the hydrogen atom. So we're assuming we have a free atom here. And as you can see, we have an electron that is in orbit around the nucleus, which has a proton inside, a positive charge. Electron has negative charge at a radial distance r. Now, for this one, when we solve the Schrodinger's equation, the solution of Schrodinger's equation in quantum mechanics is going to give us the quantization of angular momentum of electrons. So that will be an important result we will use in order to get the possible values of magnetic moment of an atom. So the solution leads to quantization of the angular momentum of electrons. And therefore, so if you accept this result, what we will find is that therefore the atomic dipole moments can only have certain orientations that is with respect to an external field. Of course, we're talking about a magnetic field in this case. So if you write the potential energy of this electron as a function of the radial distance r from the nucleus, this is minus e squared over 4 pi epsilon 0 r. Why? Because the electron has minus e charge, the proton has plus e charge, so we have a minus e squared over 4 pi epsilon 0 r. Epsilon 0 is permittivity of free space, e is the electron charge. So this is the potential energy. So that's the potential energy we have to use in solving Schrodinger's equation. Now if you write Schrodinger's equation, Hamiltonian operator applied to the wave function is equal to the energy times the wave function, and you can write Schrodinger's equation as momentum operator squared divided by 2m, which resembles the kinetic energy here, and potential energy operator we had applied to the wave function psi is going to give us energy times psi. And if you write this explicitly in 3 dimensions, this will be minus h bar squared over twice the mass of the electron, del squared minus e squared over 4 pi epsilon 0 r applied to psi is equal to energy times psi. So what are the solutions to Schrodinger's equation? So if you look at bound state solutions, for bound states we mean the energy is less than 0. The solution has the following form. Psi ends up having 3 quantum numbers, n, l, and m sub l, as a function of r, radial distance r, theta, polar angle, phi, azimuthal angle, and this has a radial part which gives us the quantum numbers n and l. And then we have the angular part, which has the quantum numbers L and m sub L. So this has theta and phi dependence. Okay, so these functions, the radial part and L as a function of r, these are called Laguerre functions. And the angular part, y L m sub L, polar angle, azimuthal angle phi, this gives us so-called spherical harmonics. And the probability of finding an electron in some infinitesimal region at the point, around the point r, theta, and phi is basically given by absolute value squared of the wave function. So that's the physical meaning of the wave function. Psi n l m sub l is a function of r, theta, and phi squared. This gives us the probability of finding an electron in the region r theta, or let's say in the vicinity of the point r theta phi. So r theta phi, this is basically spherical coordinates describing the position of a point. And regarding the Laguerre functions, one thing we have to know is that as n increases, the wave function extends farther away from the nucleus. So the Laguerre functions basically give us the following important result. As the quantum number n increases, the wave function psi extends further away from the nucleus. So you can think of having an electron cloud, and the cloud is getting wider and wider as the quantum number n is increasing, and that is basically described by Laguerre functions. On the other hand, the spherical harmonics is telling us the angular dependence of psi. So this is giving us a description of the angular dependence of the wave function. Now here you can see a drawing of spherical harmonics by Inigo Quiles, and these are s orbitals, p orbitals, d orbitals, and f orbitals. And so this is a nice visualization of how the spherical harmonics work. So this gives you a distribution, or it gives you the region in which the electron is expected to be in these orbitals. Okay, so let's talk about the quantum numbers that we see in n and l we see in the radial part, and l and m sub l we see in the angular part, which is the spherical harmonics. So the quantum numbers that arise from solution of the Schrödinger equation for the hydrogen atom, we have N, we have L, and we have M sub L. Okay, so N is called the principal quantum number. And N can take values 1, 2, 3, etc. And L is called the orbital angular momentum quantum number. And it can take values 0, 1, 2, all the way up to n minus 1. And we have M sub L, which is the magnetic quantum number. And this can take values starting from minus L all the way up to L minus 1 and L. So we have a set of three quantum numbers that arise from solving Schrodinger's equation for the hydrogen atom, and we can list them as follows: N, L, and M sub L, where N can take values, integer values 1, 2, 3, etc. And L, orbital angular momentum quantum number, takes values 0, 1, 2, all the way up to n minus 1. And we have the magnetic quantum number M sub L, which can take values minus L plus 1, etc., all the way up to L. Okay, so we have solved, well, basically we have a review of the results for the hydrogen atom. We see that the solution of the Schrodinger's equation, by considering the potential energy of the electron in the presence of a proton at a radial distance r, minus e square over 4 pi epsilon 0 r, by writing the Hamiltonian operator, momentum operator square, divided by twice the mass of the electron plus the potential energy operator applied to psi, gives us energy times psi, energy levels. And writing it explicitly, minus h bar square del square over 2m minus e square over 4 pi epsilon 0 r applied to the wave function gives us the Schrodinger's equation for energy times psi. And for bound states, for negative energy states, the solution has two parts: the radial part, Laguerre functions, the angular part, which is the spherical harmonics. The radial part gives us quantum numbers N, L, principal quantum number, and orbital angular momentum quantum number. And the spherical harmonics give us the quantum numbers L and M sub L, the angular momentum quantum number, and the magnetic quantum number. The amplitude of the wave function squared gives us the probability of finding an electron in the vicinity of the point r, theta, and phi, in an infinitesimal region around this point. And the Laguerre functions behave in such a way that as the principal quantum number increases, the wave function extends further away from the nucleus, so the electron cloud is getting bigger. The spherical harmonics gives us the angular dependence, and here is a graphical illustration of the solutions. You can see S, P, D, and F orbitals. And the quantum numbers that arise are The principal quantum number, which can take integer values 1, 2, 3, etc. Orbital angular momentum quantum number 0, 1, 2 to n minus 1, and magnetic quantum number minus L all the way up to plus L integer values.